topic of the day today is kinematics. You say, yeah, we've done that before, we got this. And the answer is yes, you do. You know this stuff. We're just going to throw, like I said, a little twist on things. Life is going to be fine. You just need to keep it in your head, okay? So here we go. When you hear the word kinematics, what do you think of now? What's the thing that pops in your brain now?
Motion.
Equations, right? And motion. So we're talking about how to describe the motion of an object. So last semester we talked about these things. We talked about kinematics. I didn't label it this way, but really what we were talking about was translational kinematics. Okay? And today we're going to add to that tree a branch for rotational. Okay? So basic definitions, that's where we started when we did translational kinematics back in August, September. Okay? The first piece that we defined when we were talking about translational kinematics was displacement. What letter did we use to mark displacement? Delta X or D. I mean, there were a few different choices, right? I'm going to go ahead and write delta X. But you can use whatever makes sense to you. Displacement means starting from one place, ending at another place, right? So it's like X initial, X final, you subtract them, you get the delta X, life is good. When we're talking about rotational kinematics, we're going to do the same kind of deal. We're going to talk about going through some angle, theta. We know theta, right? You've met theta before. You recognize that. No big deal. We got that, right? It's all good. A couple of little things about theta just to kind of keep in mind. Theta has direction as well. I'm not going to get all hung up putting vector signs over things, but these do have direction. Okay, let's be really clear about that, okay? In fact, you know what? Let's go ahead and put some vector hats on. It will make us feel better in the long run. So yes, they do have direction. Positive angles are measured generally from the x-axis, and they're measured in what direction? Counterclockwise, just like it was for torque, right? It's all the same deal. Does it have to be positive as counterclockwise? No. You can decide that clockwise is positive, just like when I'm dropping my frog, I could have decided that down is positive. I can do it. It's all good as long as you stay consistent, it doesn't matter. Okay? The units that we measured translational displacement in were what?
Meter.
Yeah. And the units that we're going to measure our angle theta in, you can use degrees, but most of us won't. And so if you want to be like the cool kids, right, then what we're going to do is to use radians. Okay?
No signal source detect.
I don't know.
The computer went off. And then it just
Okay, it'll be fine. It does that sometimes, right? Are you used to that now? Yeah. It's okay, Donald. I think you can handle it. Now, for some of you, radians are like really no big deal. You've been dealing with them for a long time. Like, you get it, no problem. I remember when I first learned radians, I was like, that's kind of weird because we've always done things in degrees. So I'm going to talk about radians for just a second, just to make sure that everybody's feeling okay about them. If you have questions, if you want to know more, please ask. But just to be really clear about what radians are, it's not a big deal, okay? The word radian just means ratio. That's all it means. That's all it is. And a radian is defined as the arc length around a part of a circle divided by the radius. Okay? So when we talk about radians, if we use a unit circle and we draw an angle up like this, maybe it's a little bit higher if we're going all the way to pi. Or, excuse me, not, but let me just say it this, to one radian. A radian is the ratio of the arc length, so this part here, along the circumference, divided by the radius. And if this ratio of this thing to this thing is 1, that's 1 radian. Does that make sense? Okay. If you have 2 radians, that means that this is twice as long as that one. Okay? It just so happens, and the reason that pi always comes up when we start talking about radians is because if I go all the way over here, the ratio between the arc length and the radius is what? Pi is 3.14. It just happens to be that way. It's kind of like a magical thing. If you go all the way around, the circle, you then have a distance of 2 pi r, right? We know that that's how you find the circumference of a circle. And your radius is r. Oops. Go away. So 2 pi radians are equal to 360 degrees. So if you are really stuck in degree world and that's just how your brain works, then if you need to, at least as we start, you can think of things in terms of degrees. You can convert it to degrees, but then you need to convert it back, okay? My guess is that as you do that more and more, you're going to be like, you know what, this is silly. Let's just live in the radian world because we can, okay? Is everybody okay with that?
Yes.
Okay. Anybody having radian issues, or we're okay? Sweet. Okay. So there you go. That's displacement. That was fun. After we talk about displacement for a while, we get a little tired of that. We want to know about displacement over time, right? Displacement over time is also known as
velocity.
Yeah, it is. And in translational motion, velocity is marked with a Come on, friends. This is stuff you should know. You all know this. It doesn't. You don't have to just listen to Addison. I mean, really, who wants to just listen to Addison?
Nobody.
Right. That's what I'm saying.
Even I know.
Even Addison doesn't want to just listen to him, right? That's what we're saying. Velocity is defined as displacement over time. This is translational velocity. This is how far you're going in a straight line divided by how long it takes you to get there. We do the same deal when we're talking about angular velocity. Angular velocity is marked, so all of the angular stuff is going to be in Greek letters. Remember we had the tau for torque, right? That was just the beginning. That's just like opening up the can of worms. Here we go. The velocity is marked with the letter omega. So to be very clear, this is not a W. It's not a curly W. It's not a little funny W. It is
Omega.
omega. Omega is the last letter of the Greek alphabet. That's the little omega. Okay? So if you need to label it, that's totally fine. Omega in Roman letters is spelled O-M-E-G-A. If you need to remember how to say it. Okay? And just like the translational cousin, it's going to be displacement over time. So omega is delta theta over t. It's the same thing. Does that make sense? Okay. Now, a couple of other little things about velocity. When we're talking about translational velocity, we know that the units are meters per second, right? We're just kind of getting ourselves into our happy place. And then we're going to move over here, and we're going to say, okay, well, in that case, then, the units for omega are going to be in what?
Radians per second.
Yeah. Now, a couple of things about angular velocity or rotational velocity. So I've been kind of using those words interchangeably, and I want to make sure that you're aware that those are okay to do, or that's okay to do. So this omega thing sometimes is called rotational velocity. I can't spell. Sometimes it's called angular velocity. And sometimes it goes by one other name. And the other name comes from the idea that this radian thing, so radians are funny because a radian isn't really a unit. Did you know that? A radian isn't really a unit because if you look at how it's defined, it's S over R. What's S measured in? It's a distance, right? So meters or centimeters or something. And if your arc length is measured in meters, what's your r going to be measured in? Meters. So you've got meters divided by meters, which is what? Nothing. It's just a ratio. Okay? So this idea of radians and the fact that we talk about a certain number of radians means nothing. Okay? Shh. It's really not a unit. Which is kind of weird, but we use it that kind of as a placeholder. Sometimes we'll use it as a placeholder here saying radians per second, but the shh, don't tell anybody thing is that radians really don't exist. They don't mean anything. So instead of writing radians per second, you can just write this as 1 over seconds. And we've seen 1 over seconds before. 1 over seconds are just what?
Hertz.
Hertz. Hertz is a measure of frequency, right? Does that sound familiar? Yeah, we talked about that like 150 years ago. Oh, wait, like last week when we struck the tuning fork, right? 256 hertz. It's the same thing. This all fits together. So sometimes instead of calling it rotational velocity or angular velocity, sometimes they'll call this angular frequency. And I'm not trying to tell you that to overwhelm you. I'm really telling you that so if you see that, you're not like, what the heck?
So
That's
like,
super scary.
if we get an answer on on something that we have to label it and it comes out as radians, like
Radians per second?
Radians per second. If we just label it as hertz, then
Here's what I would generally do. Generally, I would leave it as radians per second because that's what you usually are going to use. I'm just letting you know that now and then they will use them interchangeably.
Okay.
Does that make sense? So in general, I would still leave it as radians per second. And radians, well, they're not really a unit. They still mean something, right?
Gotcha.
So it's not like you have to get rid of it. It's just, I just wanted to point it out that it really, it's just a ratio, okay? Is that okay with everybody? Okay. All right. So before we move on and keep going, because you can probably anticipate that after we do displacement and velocity, something else is going to come up next. But before we do that, I want to try a problem real quick. This is kind of just a thinker problem. It's a very practical problem if you have siblings or if you have other small children that you used to play with when you were small. I'm guessing that you probably, well, maybe had an argument with them about this while riding a carousel or a merry-go-round or some similar thing. So take a look up here for a sec.
Oh yeah, that was like.
Am I bringing up bad memories for you?
Yeah.
Sorry. Suck it up and deal. All right, read and answer it in your head, and then I'll let you talk. Are you ready to discuss?
Yes.
Go. All right. What you got? Not you. You talk a lot. This table. What does this table say? For A.
A is the horse.
The horse. Why?
Because it's moving a further distance in meters over time.
Same time? Longer distance? That means linear speed is bigger, yes?
Yeah.
Jack, what do you guys say for B? Neither. Why? Yeah? So what? Angle is the same? Same angle, same time? Same omega, right? Yeah, yeah. So you could say neither. You could say both. You could, I guess it depends on if you're like feeling optimistic or pessimistic that day, right? Yeah, yeah. But they'll have the same omega. Life is good? Okay. All right. I'm going to pause for just a minute. Keep cruising. All right. So, we did displacement. We talked about velocity. What do you anticipate may come next?
Acceleration.
Oh, you guys are so good. And the concept of acceleration is really not that hard, right? We understand that acceleration for translational motion... Go away, please. Oh, you silly thing. Whatever. Acceleration is what? Change in velocity over time. We know that. So if you can follow any patterns here, you may expect that angular acceleration or rotational acceleration is going to be the change in what now?
Rotational velocity.
Rotational velocity, angular frequency over time, right? Yeah. It's marked with the letter alpha. Alpha is the first letter in the Greek alphabet. It is not the fishy thing. Okay? It's not the funny A. It has a name. Its name is alpha. Okay? And it is the change in omega over time. Now I have been putting these vector signs on here. Vector sign means that it has magnitude and direction. So we just need to kind of keep that in our brains. What does it mean to have a positive omega? What does it mean to have a positive alpha? Right, we need to kind of keep that in our heads. We'll get there. We're going to talk about that a little bit more. I just want to make sure it made sense. Units for translational acceleration?
Frequency per second.
Come on. Okay, hold on. I need everybody's brains on. This is not a hard question. Translational acceleration. What are the units?
Radians per second.
Okay, there we go. Translational. Oh, okay. Now, I want everybody to take a look up here because I'm going to ask you to say it all together again. Units for alpha. Think, 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 think.
Radians per second squared.
What's it going to be?
Radians per second squared.
Yeah. Oops, I don't know why I keep putting a curly thing there. There we go.
Well, can you call it hertz squared too?
Yeah, that's my question.
No,
Oh.
Yeah, that's
No.
weird.
no. Nobody does that.
Oh, okay.
Nobody's crazy.
Nobody does that.
Think about it.
No, the only time that we really use that is just in terms of that frequency thing. Just knowing that we call it frequency sometimes. Life is okay so far? Okay. I want to try a couple of questions. We're just going to kind of apply this stuff and then we'll do a couple more little things. We're doing great. All right, let's take a look here. There are a lot of words. I tried to make them big so that you can see them. So there are two questions here, A and B, or 1 and 2, or whatever you want to call them. I want you to work on this by yourself first, and then I'll give you a minute to discuss. Okay, let me see your boards.
I'll be in Masonic.
You know what?
What did you say?
Because I'm being
Let me
smart.
see your boards. Let me see them. Let me see them.
Objectify me.
I'm commenting.
Some people have more than one answer. Some people only
I
have
like
one
it there.
answer.
I'm just confused.
Wait.
Which one are we answering?
I want the first one. Oh, I wanted both, but
Oh, I'm
it's okay.
sorry.
That's okay. Okay, put them down. Cool. All right, so I think we were there more or less, but I want to make sure that it makes sense because I heard some kind of, I don't know, some grumblings and things. Which sets can occur only if the rigid body rotates through more than 180 degrees? So really, we're saying that delta theta equals 180. Ew, it's in degrees. How many radians is that?
Pi.
Pi radians, right? Everybody okay with that? So pi is 3.14, right? So we need to figure out how many radians each of these is. Well, how many radians is this one going through?
3.
3 radians, right? 6 minus 3 is 3. How many radians is this one going through?
2.
2. How many is this one going through?
4.
4. Is that okay with everybody?
Yeah.
Which one of those, 4, 2, or 3, is bigger than 3.14?
C.
Just this one. Is that okay? I can draw this out too if that would be helpful. Would that be helpful for people?
Yeah.
Yes? Okay, so if we draw it out and we make pictures of it, for this first one, where is 3 radians?
It's at. Oh, it's a little bit above the y at the x-axis on the negative side.
On the negative side, right? It's somewhere over here-ish. Okay? That is about 3 radians. Okay? Where is 6 radians?
It's a little bit below the x-axis on the positive side.
Yeah, because this is pi and this is 2 pi, right? So if you kind of have to keep that in your head, pi is going to be a little over 3 and 2 pi is going to be a little over 6. A little more than the amount here, right? So it's going to live somewhere down here. Does that make sense? This one probably should be a little closer. If we're being really honest with ourselves. Something like that maybe. And then this one's going to be over here somewhere like this. And so this is the angle delta theta. And is that bigger than 180?
No.
No. We can do the same thing for the second one. Let's just kind of go through this. Sometimes it's nice to actually just look at this and see what's going on. So 1 radian up or 1 radian down. So that means that the ratio between this arc and this length is going to be the same. So it's going to live somewhere over here-ish. Does that make sense? Okay. What is 90 degrees equivalent to in radians? Pi over 2. So we kind of think about that. Pi over 2 is going to be a little more than 1, right? Yeah? So it's going to live somewhere over here. Oops, I guess it's a little, well, that's about right. There's positive 1. That's the final. The initial is over, oops, the same distance down. Like this. And so that would be your delta theta. Is that bigger than 180? No. So we could use process of elimination, but let's just kind of talk it through one more time because we can. So if we start at 1 radian, which was up here, and we end at 5 radians, where is 5 radians going to be?
It's like a little bit to the right of the y-axis on the negative side.
Here-ish?
Mm-hmm.
And these are, I mean, obviously we're just kind of approximating. But we can definitely see that that delta theta is bigger than 180, right? So if drawing it out helps you, if that kind of helps you to internalize what it looks like, great. Otherwise, you can just say, okay, well, I know that I have to get pi. This one's bigger than pi. So we're good. All right. The second part said, suppose that this change in angular position for each pair of values occurred in 1 second. Which choice represents the lowest average angular speed? Angular speed is marked with what letter?
Gamma. I mean, sorry, omega.
Okay, Addison's not allowed to be loud anymore because I want you to talk too. So I'm going to ask the question one more time. What letter are we using for angular speed?
Omega.
Okay, thanks. And omega is delta theta over t, right? How do the t's compare in each of these cases?
They're all the same.
Same. So to have the smallest omega, you need the smallest theta, which is going to be which one? Is that okay? Okay, sweet. All right. Questions on that? We happy? Awesome. All right. You've noticed a bunch of parallels, yes? Between the translational stuff and the rotational. We're just going to do some more of it. Here we go. Yes, graphing. I've missed it so much. All right. Angular velocity time graph, angular acceleration versus time graph. Here we've got an angular velocity versus time graph. So literally what's happening here? Can somebody talk me through what's going on? This is omega. So omega is the angular speed, the speed with which it's going in a circle. Go, Ann.
This is going clockwise around the circle.
Uh-huh.
No,
Counterclockwise around the circle.
Yeah, and it's speeding up at first, and then it kind of goes at an average velocity, and then it
Slows down, but it's still going in the same direction, right? Does that make sense to everybody? So it's going in a counterclockwise direction, and then it's going at a constant speed, and then it's slowing down, but it's still going in that same direction. I want you to draw the acceleration graph. It's the same process as we used when we were doing translational stuff. Go ahead and draw it by yourself first. I'll give you about, 45 seconds, and then I'll let you discuss and put it on your boards. Okay? On the same page, it looks like we're getting this, right? The same process happens if we look at the definition for alpha. Alpha is change in omega over t, right? Slope. Slope, right? It's just slope. So the value of the slope is going to give you the value of the alpha. We've got a positive slope here for 2 seconds. And then it's a 0 slope. And then it's a negative slope for 1 second or 1 unit of time. And then it's back to 0. The one thing that I noticed on a few of them, make sure that it's very clear that this slope and this slope have different magnitudes. Does that make sense? Because this one, the slope here, the magnitude is much less than the magnitude here. So you want to make sure that this distance and this distance are clearly different. Life is good? Ready for another one? Yes! All right. So this one is a little bit more than the other. Let me make sure that you understand what's going on before I leave you to figure it out. It says that you have a weight tied to a rope wrapped around a pulley. So here's your pulley. Here's your little weight. It's like the one that was sitting on the balance earlier. The part, right? That's how it works. The pulley is initially rotating counterclockwise, pulling the weight up. The tension in the rope creates a torque, oh, we know that word, on the pulley, and that opposes the rotation. The weight slows down, stops momentarily, and then moves back down. Can you imagine this happening?
Yeah.
Okay, so it's rotating, it stops, and then it starts rotating the other way. Graph the angular velocity versus time for the period from the initial instant to when it comes back down to the same height. So it's going to go up and then come back down to this place. And then graph the angular acceleration. Okay. I'm going to let you think I'm just going to let you think for like 45 seconds again, and then I'll let you discuss, and then I want to see it on the boards. But I'd rather that everybody write it on paper first so that you're not just going with somebody's answer on the board. So this is yours. I see a couple of boards. Oh. I see another board.
Oh, wait a minute. With
Got a couple of them still coming.
Other way around.
Yeah.
No, it's not.
Yeah, that's.
What are your axes there,
Okay,
Peter?
that's right. Put that there. You need to have that one all the way at 0. And then another one at 0.
Well, initially I did this.
Oh, hey, that acceleration is negative.
Why don't you bring your boards up? Whoever has the board, bring it on up.
That should be on the same plane as that guy.
When you're talking about this, it's the same process. So we've got some positive velocity, angular velocity now. It goes through 0 and it starts speeding up in the negative direction. This is exactly the same graph, if that was a V, that you would have if you take the frog and you throw him up in the air, right? He stops for just a moment, and then he comes back down, okay? The acceleration is going to be constant and negative. Even if I don't really understand what the acceleration is doing, can I get that information right from this graph?
Uh-huh.
Yeah, because the values for alpha are going to be the what from the omega graph? Slope. Constant and negative. Constant and negative. Right? Is that okay?
We were right. We just.
You can also figure this out, friends. This is just a little hint. What does this mass do? What's it doing?
Move it up and down.
It goes up, and then it comes back down, right? Just like the frog did. It's the same process. This translational business and this rotational business are very, very well intertwined. So well intertwined that we actually can relate them very, very clearly. So here we go. So we're going to do next. We're going to put them all together. Here we go. Zoe, would you do me a favor? Can you turn the front lights on for me? I'm afraid I'm going to zone out if I don't have them. Do you remember that we first started defining theta as S, which was just the arc length, which is really the translational displacement? Is that okay? So I'm going to call that delta x over t. Is that okay with everybody? Okay? So really, I'm going to move this over because I feel like I want it further over here. If I solve that for delta x, I get delta x is equal to, oops, not t. You guys agree with me, and you shouldn't. Who agreed with me? Jenny, was that you? Michael, did you agree with me? What should that be, friends?
Radius.
Yeah! You gotta keep me honest, Jack Nogla. Come on now. You're like, yeah, sure, that sounds good. No! Wrong! Wrong answer. This is the right answer, right? Okay. very dangerous. That's not a good plan. Are we okay with this?
Yeah.
Okay. I hope so. I hope so. All right. I could write this as r times theta. Is that okay? Or r times delta theta? Okay. I know that velocity is displacement over time. And so all I'm going to do now, friends, because now I've got a nice relationship with no denominators, yay, no denominators. I want to see if I can get a relationship for V that has omega in it. And guess what? I can, because I'm so cool. Look, V, bless you, is equal to r times theta, r times delta theta, I suppose, in this case, if we're doing the change in over t. Is that okay with everybody? And Alex says, hey, Miss Carbeling, look how cool that is. You've got delta theta over delta t. Whoa!
That's amazing.
Addison gets excited too. Esteban gets excited. Everybody's excited. It's like a party because we know that delta theta over delta t is what?
Omega.
Whoa! So we can say that velocity, translational velocity, I'm not going to put vector hats on that because it's not quite right, is equal to r times omega. So if you know the angular velocity and you know how far out something is on the circle, then you can figure out its translational velocity without doing any other work. That's pretty sweet. What's up?
What's a good way to write omega so that I don't confuse it with the W?
Well, I don't know how you write. It depends on how you write a W. So like when I write a W, I make them pointy. The other thing I would say is to make like the second tail bigger. Does that make sense?
You can also
Yeah.
make it so that like where in the middle you can just make that a circle.
Oh yeah, like that?
Yeah.
You could do that too. Does that give you some answers?
No, because I write my W like the circle with the tail.
So then do your omega like a pointed
Then,
W.
wait, no. Then
Yeah, I
just
wouldn't recommend that because then other people are going
write
to
your
confuse.
omega like a normal W and you'll understand it.
As long as it's clear.
How often
So-
are you using normal W's in physics?
Work, but that's capital, right? We don't use little w's very often in physics. Michael, what were you going to say?
I have the tails like point in.
Oh, like kind of like a little more
We'll just like
actively pointing in, like that?
Yes.
Okay.
I shade the curvy regions and I make sure that the bottom points are pretty like thin lines, and then I make sure that dot is like an ellipse.
Or you can do that. All right, we're going to keep going because that seems like a little too much for my brain to handle. Acceleration is what? What is acceleration in regular? Like I could have asked you at the beginning of the day and you would have told me acceleration was?
Meters per second. Oh, change velocity over time.
Did I mention that Addison isn't allowed to talk anymore?
Yes.
Should have. All right. Change of velocity over time, right? So I've got velocity is omega, or is r times omega. So now I'm just going to say that acceleration is r times delta omega divided by time. And then Amanda says, but wait, everybody, look at this. This is delta omega over time. Delta omega over time, I know that. And Lindy's like, me too, and Brian's like, me too. What is that?
Alpha.
Oh. So that's pretty cute because then we've got A is equal to R times alpha. So now you've got relationships between each of these things, the translational version and the rotational version. And what is it that connects them?
Radians.
The radius. How far you are out on the circle. Okay? That's all that you need. Is that okay? All right. We're going to take that and use it. Here we go. I'm going to let you work for a minute. Then I'm going to let you discuss, and you need to discuss this while we're doing it, because we've got a couple more things we still have to do. Fair? All right. Here we go. We've got hollow spheres that are not drawn to scale. They're rolling at a constant rate without slipping. You'll care why later. The spheres have the same mass, but their radii, as well as their linear and angular speeds, vary. So I'm going to zoom this in so you can see it. The question asks you to rank the radius of the spheres. Okay? So this is you in your brain for a moment, and then I'll let you discuss and put it on boards. Let's see them. Let me see your boards. Okay, you guys need to get on it. Come on. Like, seriously.
We all had the answer, we just didn't write it down.
Do it. That's why I asked if you were ready. Okay, the people that are ready and right. Sweet. All right, does it make sense? Awesome. You guys are rocking. I love it. I love it. Okay. So, we've been seeing parallels all day, right? Between translational and rotational. Have you noticed that I keep saying this, right? It just keeps going. So, there's one more thing that I want to tell you. I don't know if you remember last semester that we had a day when we got to live through something that many of you have been waiting for. That day when we actually derived those 4 kinematics equations. Do you remember? That was so much fun. And we did it, and we pounded them through it. It only took us like 5 minutes, right? Here's the deal. No, we're not going to actually go through it. But all of the translational equations, those 4 big ones, we can write rotational equivalents. Okay? So I just want to write them down with you. Here we go. So there's one translational equation that says something like VF is equal to VI plus AT. We can write a rotational equivalent. Every time you see a V, you're going to write a what? Every time you see a V, you're going to write an omega. Every time you see an A, you're going to write alpha. Every time you see an X, you're going to write a delta. And every time you see a T, you're going to write a T. Yeah. So this is going to be omega final is equal to omega initial plus alpha times time. Okay. We'll write down a couple more. If you've got X is equal to VIT plus 1/2 AT squared, or like VF squared is equal to VI squared plus 2A delta X, go ahead and write the rotational equivalents of those equations. Got them? Compare with your neighbors. Make sure they agree with you. And then I'm going to put another problem up here for you to work on before it's time to go.
I picked it up and then I pulled over the.
Omega final square.
All right.
Omega initial square plus 2
One more
alpha
problem
delta
for you to
T.
work on. A bicycle wheel is rotational motion, right? Rotational motion that causes you to have translational motion. Are you with me there? So the bike wheel rotates and you move. It's kind of a nice system. A bicycle slows down uniformly from an initial velocity of 8.4 meters per second to rest over a distance of 115 meters. Each wheel has an overall diameter of 68 centimeters. Part A says to determine the angular velocity of the wheel at the beginning. Part B asks you to find the total number of revolutions each wheel rotates in coming to rest. C asks for the angular acceleration, and B asks for the time. Probably won't get through all of this right now, but I want you to give it a shot. Get started. We'll finish with this one next time.
Bye.